It's a pleasure to introduce Professor David Leep from the University of Kentucky. Professor Leep and I have a special connection. We had the same PhD advisor, the late Professor Don Lewis. So it's a pleasure to introduce my older mathematical brother, Professor David Leep, that's going to talk to us today about systems of quadratic forms of complete discretely valued fields. Thank you, David, for accepting our invitation.
All right. Well, thank you very much for inviting me to this conference. It would be nice to attend in person, but I understand. All right, so I'm going to be talking about systems of quadratic forms. Here is the basic point of view. It is interesting to know whether a quadratic form with coefficients coming from some field, say, has a non-trivial zero. Famous examples, an easy one would be a quadratic form with coefficients in a finite field always has a non-trivial zero if the quadratic form has at least 3 variables. That's easy to prove. A more difficult theorem to prove is a quadratic form with coefficients in an algebraic number field. Let's just say the rational numbers. A quadratic form with coefficients in the rational numbers has a non-trivial zero as long as the number of variables is at least 5 and the quadratic form is indefinite. That is, has a real solution. There are lots of other questions that can be asked about lots of other interesting fields that come up in number theory and algebraic geometry. One way to attack this problem is via systems of quadratic form. I will be talking about in the first part of the talk, and then concentrating more for the question about systems of quadratic forms over complete discretely valued fields to be defined later in the talk. All right, so K is going to be a field, and F1 through FR will be a system of R quadratic forms in n variables with coefficients in K, as I've written here. Just some very basic terminology. The system F1 through FR is said to be isotropic over K if there is a vector A. So in other words, if there's a non-trivial solution, A1 through AN, lying in K, not the zero vector, so it's non-trivial solution, such that Fi of A is equal to 0 for each I going from 1 to R. So that's an isotropic system. The system is anisotropic if it's not isotropic over K. And I want to define the following notation, which I'll be using throughout here. U sub K of R. It's the supremum of all integers n, such that there exists an anisotropic system, F1 through FR over K and n variables. So in other words, if the number of variables n is bigger than U sub K of R, that would say that every system of R quadratic forms in n variables having coefficients in K has a non-trivial zero. So to put this in context, U sub K of 1, so this is a system of 1 quadratic form, this corresponds to the classical U invariant of a field K. So this has been studied for well over 50 years or more, depending on how you look at things. The U invariant is if I have enough variables, then 1 quadratic form will have a non-trivial zero. So I'm looking at systems of R quadratic forms. Okay, so the problem is compute this number for interesting fields K. For me, a field K is interesting if it arises naturally somehow in number theory or algebraic geometry. So that's an interesting field, okay? So first, let's take care of an uninteresting field. For this topic, an uninteresting field would be the real numbers, because x1 squared plus x2 squared plus ... xn squared would be anisotropic over the real numbers or any formally real field for every n greater than or equal to 1. It's positive definite. It would only have the trivial zero. So therefore, for this topic, formally real fields, such as the real numbers or any real closed field, would be uninteresting. Now, I'll point out that going in a completely different direction, some of what I'm discussing today can be modified and made interesting to discuss over formally real fields, but not what I'm doing today. So therefore, today and only today, the real numbers is uninteresting. Okay, so interesting fields might consist of the complex numbers or any algebraically closed field, a finite field, Q sub p, the field of p-adic numbers, a non-real number field, that would be a number field having no real embeddings, and function fields over these fields. And just a point, it's not important for today's talk, a field K can be characterized as non-real if and only if -1 can be written as a sum of squares in the field. It's a theorem that condition is equivalent to saying that the field has no ordering. So anyway, so we're interested in interesting non-real fields. The following theorem motivates the study of systems of quadratic forms and even systems of homogeneous forms of higher degree. But I'm going to just stick to systems of quadratic forms here. This is a theorem, very mysterious. It was proved independently by lots of people during many different decades. Sen in the 1930s, Albert, A.A. Albert in the late 1930s, Karlitz in the late 1940s, Lang, most famously in his dissertation around 51. And they were all proved independently in various versions, various levels of generality. So therefore, what I'm about to state, really you couldn't find anywhere in the literature, but it all comes from these people here. And it says the following. Let me just show more here. Suppose, so I'm right here, suppose there exists a positive number A, positive real number A, such that U sub k of R is less than or equal to AR for all R greater than or equal to 1. So in other words, U sub k of R is bounded by a linear function of R for all R. Suppose that. Let L over K be a field extension with transcendence degree L over K, where the transcendence degree is equal to M greater than or equal to 0. So remember, transcendence degree 0 would just mean an algebraic extension. Then, with this hypothesis, then 1, U sub L of R is less than or equal to 2 to the M times AR for all R greater than or equal to 1. So in other words, with this hypothesis right here, suddenly you have lots of information about systems of quadratic forms over function fields of any transcendence degree over the field. Now, that's statement number 1. Statement 2 is fine-tuning it. And statement 2 is, both statements are useful in different contexts. Suppose we assume just a little bit more. Suppose L over K is finitely generated, transcendence degree M. Suppose that U sub K of R equals A times R for all R greater than or equal to 1. Then, in fact, for trivial reasons, capital A would have to equal U sub K of 1, the U invariant. And we actually have equality here. U sub L of R equals 2 to the M times AR. So in other words, and this is for all R greater than or equal to 1 and all M greater than or equal to 1. And I'll just say right here, that's not a typo. I deliberately left out M equals 0 because in the algebraic case, you can't be quite that precise. So in particular, U sub L of 1, that would be just the U invariant for one quadratic form, is equal to 2 to the M times the U invariant of K. Well, let me give one example then. So in number 2, for example, if I take just the rational function field in M variables under the hypotheses in 2, we would have a precise value for the U invariant of this rational function field. It would be this. And this, I will say, this does hold for all M greater than or equal to 0. Now, so this is great. Suddenly we know everything about solving systems of quadratic forms. At least we know about the existence of solutions. All that matters, and this is the hard part, is the hypothesis. So what we need to know is what fields have this, satisfy this hypothesis that this U sub k of R, the U invariant for systems of quadratic forms, for which non-real fields is it true that this invariant grows linearly in R? So that's the hard question. And once you have this very difficult hypothesis, then all of these results flow easily. The proofs turn out to be rather elementary, and you're in great shape. All right, so that's the question I asked here. For which non-real fields does the U invariant for systems is it bounded linearly? All right, so let's look at two examples, two quote unquote well-known easy examples. One, suppose K is an algebraically closed field, such as the complex numbers, then it is a theorem that U sub k of R equals R for every R greater than or equal to 1. In other words, we can take capital A equals 1. This would be a theorem in algebraic geometry. Algebraic geometers would simply say, by dimension theory, it follows easily. Okay, so you have to fill in the details, but it's a well-known basic theorem in algebraic geometry. The second good example is suppose K is a finite field. Then it is a theorem that U sub k of R equals 2R for every R greater than or equal to 1. So in other words, we can take capital A equals 2, and this follows easily from the so-called Chevalley warning theorem. And I forgot to write here, but it's obvious, for all R greater than or equal to 1. Okay. Now, in terms of the basic examples, so if we start with an algebraically closed field, or if we start with a finite field, then we have a whole infinite family of fields where we know about about the existence of solutions of systems of quadratic forms, and namely all the function fields over these fields. Okay, now there's one more, those are sort of the easy cases. Anything else tends to be harder to prove. There is one more class of fields. The proof is more difficult. There's a theorem of Greenberg. And here I'm stating a very special case of a wonderful theorem of Greenberg proved in the mid-1960s. Suppose there exists a positive number A, it's the same hypothesis. Suppose there exists a positive real number A such that we have this hypothesis bounded by linear function for the U invariant. Then the same holds true for the power series field. So K double parentheses T would stand for, I could call it the field of formal power series or the field of Laurent series. It's the fraction field of the formal power series ring, K double bracket T. And it says that the U invariant for systems of R quadratic forms over such a field is bounded by 2AR. So in other words, the constant A here has to be doubled to 2A. And this is for all R greater than or equal to 1. As I say, Greenberg's theorem is far more general, but this is what I need for today. This proof, let's see, do I say it here? No. This proof actually, in the case when K is a finite field, Lang proved this using some sort of compactness argument I won't go through today. When K is a K is an infinite field, more work is required, and the proof is more extensive. It's not quite as obvious. Okay. Now, I've been talking about this hypothesis right here. It's hard to verify, and yet, ironically, we know of no examples where it is not satisfied. This is a very peculiar situation. So it says here, no example is known where this value is actually greater than 2 times this constant times R. So even though we can't prove prove anything in general, or it's very hard to, we know of no counterexamples. What is known? Well, it's always true that the U invariant for systems of R quadratic forms, for trivial reasons, it's always greater than the U invariant times R. And I showed in the 1980s, there is a quadratic bound, R squared plus R over 2 times the U invariant. So that turns out to be a very elementary proof, and getting the quadratic bound to a linear bound, well, we don't know if it holds or not. However, we do know that there exist fields K where the U invariant for systems of R quadratic forms is greater than this number times R for all R greater than or equal to 3. And an example is K is the quadratic closure of the rational numbers. One can prove this. It takes a bit of work, but not too hard. And yet we don't know of any example, as I said up here, where we would have strict inequality. We don't know if it's true or not. So therefore, let's just go ahead for the record, state a conjecture. It would be nice if U sub K of R, if this is always bounded by this constant. So maybe the U invariant for systems of R quadratic forms, perhaps it's always bounded in a linear way by this constant. That would be a great theorem, but there isn't that much evidence for it, but there's certainly no evidence against it. Okay, so for general fields, this is sort of the situation. The basic facts that are known. I want to now jump to complete discretely valued fields. I'm going to briefly give some definitions. Before I do, I'll just say, why am I jumping to this? In terms of interesting fields in number theory, the first set of examples that we don't know would be for p-adic numbers. We know that systems of quadratic forms over finite fields, by the Chevalley theorem, we have a theorem. Over power series fields, we have a theorem. Sort of the next case to consider would be p-adic fields. These are complete fields with a finite residue class field. But I want to do things a bit more generally, so let's just go through some definitions quickly. Suppose K is a field and V is a valuation. And suppose it's a non-trivial valuation, and I've just briefly recalled the definition of valuation. Those are the first 3 properties. And to be a non-trivial valuation means there exists an element A and K different from 0, such that V of A doesn't equal 0. So I want to deal with suppose I have a non-trivial valuation, and this would be called a discrete valuation because the value group is a subgroup of the integers. Now, without loss of generality, we can assume that V is surjective. The reasons are easy. I'm going to skip the reasons, but without loss of generality, any non-trivial discrete valuation, we can assume that the value group is all of Z. All right, so there's certain objects associated with such a valuation. We have O sub K, which is the ring of integers. It's those elements that have non-negative valuation. We have this maximal ideal M sub K, would be those elements whose valuation is positive. And there's going to be an element we're calling pi, such that its value V of pi is 1. Then it's straightforward to show that O sub K is a valuation ring. M sub K is the unique maximal ideal in O sub K. It's a principal ideal generated by pi. And the quotient ring, O sub K mod M sub K, we're denoting by little k or lowercase k. And that's called the residue field of this field with respect to the valuation V. And all of this information is summed up here, the sort of the 6 pieces of information. The field K, valuation V, ring of integers, maximal ideal, the A generator, and the residue field. So this is a discretely valued field, and we'll say that this is complete, so a complete discretely valued field, if the field is complete with respect to the metric topology induced by the valuation. I'm not going to define the metric topology, we don't need it. I'm just saying there is one, and it's complete if it's complete with respect to that metric topology. Okay, so it turns out complete discretely valued fields, surprisingly, can be characterized reasonably well, as you'll see in a moment. Suppose that K comma V is a complete discretely valued field. If the characteristic of the residue field equals the characteristic of the big field, so both 0 or both P, then it turns out, surprisingly maybe, that K is isomorphic to a power series field. In the case when both have characteristic 0, it's not hard to prove. And if they both have characteristic P, you have to work just a little bit harder to prove this, but you can do it. In the second case, okay, there's a theorem, but it's a little complicated. If the characteristic of the residue field is P, bigger than 0, and the characteristic of the original field, capital K, equals 0, then, well, I've bailed out here. I'm not giving the details. Then the structure of K is more complicated. Well, there's a theorem dealing with Witt vectors. It's not important for this talk, so it can be described in a rather complete way, but it's kind of complicated, but it's understood. Let's just put it that way. All right, the example, this is the best example for today's talk, would be the p-adic numbers. For every prime number p, there's a valuation v sub p from q to the integers, and the completion of q with respect to this so-called p-adic valuation is q sub p, the field of p-adic numbers. There are many ways to define q sub p, but one of them is the completion of q with respect to this valuation. And then for the notation above, the ring of integers of q sub p is usually denoted as z sub p. The maximal ideal turns out to be the ideal generated by p. That is to say, we can choose pi to be the prime number p. And the residue field k is isomorphic to z mod pz, or in other words, the finite field with p elements. I didn't write this down, but this can be generalized to any algebraic number field, to any prime ideal. You can do the same thing. There's a completion, and the same thing works. So you can talk about completions of the rational numbers or completions of any algebraic number field with respect to some prime ideal. So let's write down the following conjecture, which is of interest here. Assume this, so all of our information, assume this is a complete discretely valued field. Assume that the residue field satisfies this hypothesis for the U invariant of systems of quadratic forms, namely that the u sub little k of r is bounded by a linear function of r. Suppose that for all r greater than or equal to 1. Then the complete field, capital K, should have the same property, and but the constant a is replaced by 2a. So this is the conjecture I'm interested in. And then just as before, a more precise conjecture would be assume that I actually have equality in the residue field. Then the conjecture would be over the complete field, I also have equality for all r greater than or equal to 1. And just for the record, I'll say, what do we know in a trivial way? In statement 2, I should say in conjecture 2, in the second statement of conjecture 2, capital A necessarily has to be the U invariant. And we always have that this quantity right here is greater than or equal to this quantity. It's the other inequality, which is hard, but we want to prove equality. So this is true for trivial reasons, but I'm not going into the reasons why. The prime, no pun intended, the prime motivating example is Q sub P. Suppose K is Q sub P, so a complete field, residue field F sub P, field with P elements, then capital A equals 2, because that's what I said by the Chevalier warning theorem, that this holds by the Chevalier warning theorem. So therefore, the conjecture would be for Q sub p that the U invariant for systems of R quadratic forms over Q sub p should actually be, we know it's greater than or equal to 4R for the trivial reasons I referred to above. The conjecture is it's less than or equal to 4R, and therefore we would have equality. Okay, now let's see, before I go on, you see a little hint here of a theorem. So this question was first investigated in depth, starting really in the 1960s. When R is equal to one quadratic form, this actually goes back to Hasse, 1920s. For two quadratic forms, it was proved, I think I might be saying this later in the talk, it was proved by Birch, Lewis, and Murphy, the Lewis are my thesis advisor, Birch, Lewis, and Murphy, that this actually holds for two quadratic forms. Several years later, they then attacked the problem for three quadratic forms, and it became quite a mess. In other words, it was a very involved argument, and the published paper actually had some mistakes in it, and it was later corrected by a PhD student of Lewis. But even that argument was complicated. But basically, what the theorem said was that this conjecture is also true for R equals 3, as long as P, the prime P, is big enough. And big enough meant, well, in the original Birch-Lewis paper, they said bigger than 49. It was then corrected to bigger than 17 or bigger than 11. I'm not convinced that all the details were there. But anyway, if excluding a small number of small primes, that the conjecture was true for R equals 3. That still worked in the 1960s. In a sense, nothing happened except until really around 2010, when Heath Brown proved the following theorem. When I say nothing happened, I was able to prove this quadratic growth in the 1980s, but in terms of the linear growth of these U invariants, nothing happened until 2010. And Heath Brown proved the following theorem, that indeed U sub Q P of R equals 4R. So in other words, a system of R quadratic forms in more than 4R variables should have a non-trivial zero. What Heath Brown says, as long as P is bigger than 2R to the R. Okay, so first I'll say, yes, he did prove something a little bit more general. He proved the result for even finite extensions of QP. And then the residue field has to be bigger than 2R to the R. I'm just giving the simplest version. And it says here, Heath Brown's proof depends on the residue field K being finite. The proof doesn't generalize. So in other words, it's so heavily dependent on some kind of counting argument. There doesn't seem to be a way to generalize this to proving some version of the conjecture for complete discretely valued fields and an arbitrary residue field. Okay. So there are some things we can say about this general conjecture too, the general case. So assume K comma V is a complete discretely valued field. So indeed, in general, the conjecture does hold for one quadratic form. I have here in parentheses, Springer's theorem in quotation marks. That's because I know that Springer proved this in the 1950s when the characteristic of the residue field is not 2. I didn't have a chance to check. Did his proof go through for characteristic 2? I'm not sure, but it is known to hold in all cases. So for one quadratic form, the conjecture is true. For two quadratic forms, it's also true in general. What you do is you take the proof of the Birch-Lewis-Murphy that Birch-Lewis and Murphy gave, and it's not too hard to generalize things and make the proof go through in general for an arbitrary residue field. Okay, but other than that, for the general case, I would say nothing. We don't have other results. So I want to now discuss a strategy for proving conjecture 2. So let's make the setup here. The first part of the strategy does date back to the 1960s, but then there'll be a change. Suppose I've got F1 through FR, a system of R quadratic forms and n variables, and suppose that n is bigger than 2AR. Now, I'm assuming the hypotheses that I stated earlier in conjecture 2 about that we are assuming something about systems of quadratic forms, the U invariants, over the residue field. We are assuming knowledge of that. Well, the first thing is we can assume that F1 through FR has integer coefficients just by multiplying through by clearing the denominators. So we will always assume that the coefficients lie in O sub k, the ring of integers. Let F1 bar through FR bar denote the images under the residue field map, O sub k going to O sub k mod the maximal ideal. Our goal is to find a non-singular zero of F1 bar through FR bar over the residue field K. And I'm recalling very briefly, what is a non-singular zero? A is a non-singular zero of a system, here F1 bar through FR bar, if A has entries in the residue field and the Jacobian matrix J of A has rank R, where the Jacobian matrix is you take the partial of Fi bar with respect to Xj, that will be an R by N matrix, and you evaluate each of these partial derivatives at the vector A. If J of A has rank R, that's called a non-singular zero. And what's good about this is, if you have a non-singular zero, then Hensel's lemma implies that the system has a common non-trivial zero over the completion of O sub k, and then we're done. So you'd say, okay, all we have to do is find a non-singular zero. Unfortunately, this is really hard. And more than that, it can't always be done. So you might say, oh, so this strategy maybe isn't so good, but wait. So it is not always possible to find a non-singular zero, although it's hard to give an example, but there are examples. Well, it turns out, and again, this idea still goes back to the 1960s, it is sufficient to prove conjecture 2 for a p-adically dense subset of systems of quadratic forms when, oh yeah, there should be a period here, I'm sorry. Sorry, my iPad is too sensitive at times. And I've lost my place, hold on here. Okay, now when K is a finite, to explain why it's sufficient to look at a p-adically dense subset, when K is a finite field, this follows using a compactness argument. When K is an infinite field, we have to appeal to this theorem of Greenberg that I mentioned earlier. So it's a more difficult argument to fill in all the details, but the argument is there. Okay, which p-adically dense subset of systems? There is a p-adically dense subset of systems of quadratic forms with each Fi having integer coefficients satisfying the properties below. Let's set it up here. I'm reading right here. Let capital M be the O sub k module generated by F1 through FR. For every S between 1 and R, let G1 through GS be arbitrary elements, or arbitrary linear combinations of F1 through FR, O sub k linear combinations, where G1 bar through GS bar are linearly independent over the residue field K. Then the order of G1 bar through GS bar is at least this funny looking quantity right here. The order, and just as a quick informal definition of order, the order of a system is the least number of variables needed to write the system. So again, a very simple example is this quadratic form in 3 variables really has order 2, because by a change of variable, this is really a sum of 2 squares. Okay, so the order of a system is the least number of variables you need after some appropriate linear change, invertible linear change of variables. So what I'm saying is, one can show, and I'm certainly leaving out all the details, that there is a p-adically dense subset of systems where this funny looking condition right here is satisfied. And just to illustrate one thing, for example, if I take the case S equals R, and if I'm assuming N is bigger than 2AR, which I am from above, then the order of F1 bar through FR bar is greater than or equal to N over 2, if you look at what I have above, which is bigger than AR. So in other words, when I reduce the system of quadratic forms mod pi, it's possible that every coefficient is divisible by pi, right? And when you reduce mod pi, everything collapses to 0. Well, what we're saying is I can restrict to a dense subset of systems of quadratic forms so that when I reduce mod pi, I do not lose too many variables when I reduce mod pi. Okay, these additional properties make it easier to find non-singular zeros of F1 bar through FR bar over K. So remember I said all I had to do is find a non-singular zero, but I said, but sometimes you can't do it. If restricting to this dense subset, it makes it a lot easier, but still, it's not that easy. It turns out this is enough for R equals 1 or 2, and that's basically why the proof of conjecture 2 could be proved for R equals 1 and 2. There are already difficulties if R equals 3. The work of Birch and Lewis in the mid-1960s certainly illustrated that. But there's something, now I'm getting to newer material. Here's something that can be done. Assume the following hypotheses. Assume that the residue field K is infinite, yes. Assume that we have linear growth of the U invariant for systems of R quadratic forms in the residue field. So we are always assuming that. Assume, this looks funny, but just have to write down the condition. Assume that each S-dimensional subspace of the K span of F1 bar through FR bar has order at least this completely unmotivated quantity for every S between 1 and R. Then F1 bar through FR bar does have a non-singular zero over K. And it says the proof is technical. It is. It's technical. Okay, so this is a way to know that there is a non-singular zero. However, as we'll see in just a second, this isn't quite good enough. What I'm able to prove from this is, assume, this is the same hypothesis, assume the residue field is infinite, and we have this linear growth here and the U invariance. Then for all R greater than or equal to 1, we have this. We almost have the U invariant is less than or equal to 2AR. I have to add on an interesting constant. I wrote capital M of R for some constant M that depends only on R, but interestingly is completely independent of the field I'm working with. It turns out this is not important, but this is a concrete expression for what one can take for this M of R. So, well, we've got something here, but it's not good enough. So there's an additional idea I want to introduce. I'll write this as a lemma. Assume I have my complete discretely valued field, this first line here. Then there exists another complete discretely valued field such that, so L comma W is complete. Okay, so L is an extension of K. The valuation W on L, when restricted to K, restricts to the original valuation V. And, oh, and I need to point out, but what's interesting here is they both have the same uniformizer, but the residue field of capital L is K parentheses T, the rational function field in one variable. So it's an extension of K, where I'm extending the residue field to make it K adjoin T, the rational function field. The uniformizer pi is the same, and L contains K and is complete and extends the valuation. So it says, note that K and L have the same uniformizer, and the residue field of L is the rational function field. So all this lemma says is such a complete field exists. That's my lemma. That's not too hard to prove. Now, theorem in quotation marks. Well, because I'm being honest, I don't have a complete proof yet. It appears to be true, but I'm not, the proof is not completely there, but it's pretty darn close. And it says the following: for these two fields, K and L constructed above, the U sub L of R U invariant is greater than or equal to 2 times U sub K of R. This is tricky because the field L, I'm just gonna say it's tricky to work with. It's easy to make a mistake. So you have to be really, really careful. I'm going to say the theorem in quotation marks can be used to give a proof of conjecture 2. So this is great news. All I need to do is finish the proof of theorem in quotation marks. And I can even give the proof here. It's kind of interesting. For each j between 0 and little m, where m, this little m is going to be specified below, I define a chain of fields, capital K, which is K0, contained in K1, K2, up through K sub m, where I'm using this construction over and over. K sub j is shorthand for all of my information, same uniformizer, but the residue field is K adjoin T1 through T sub j. These are variables. So I'm applying my lemma m times. So by the theorem, in quotation marks, I have this relation between my U invariants for systems of quadratic forms. And if you put it together, you get this right here. Now, this quantity implies, using my motivating theorem from very early in the talk, this quantity implies, I'm meant to say this inequality implies this inequality for all R and M greater than or equal to 1. Now, when M is greater than or equal to 1, this residue field is infinite. So when I stated some results earlier, when a residue field had to be infinite, I'm okay because I have an infinite residue field here. All right, so what have I got? If I put everything together, U sub K of R, which is just this because K equals K0, it's less than or equal to this quantity that's coming from this right here, is less than or equal to, by a theorem from above, 2 times this quantity plus M of R over 2 to the M, which simplifies to 2AR plus M of R over 2 to the M. So you choose M large enough so that this quantity is less than 1, and then we get our result. And that's the proof. So I'll have a proof of conjecture 2, but there's still work to be done on filling in the details of this theorem. And I am going to say this is true for R equals 1 and 2. I can prove this using ad hoc methods that don't generalize. So, I mean, there's this and more. There is evidence that this thing ought to be true, but I'm still working on the details. Okay, so let me say let's suppose conjecture 2 is true. Well, in particular, the consequence would be that for Q sub p, say, the U invariant for a system of R quadratic forms actually equals 4R for all R greater than or equal to 1 without the Heath-Brown condition about P being sufficiently large, P being greater than 2R to the R. We would have this. And now there's some interesting consequences of this. And I'm going to say it this way. What about systems of cubic forms? So a lot of work has been done on this by people like Wolfgang Schmidt and then Rainer Dietmann. And it should be possible. I've done some work already. It's a lot harder, but some of these methods can be changed to work for systems of cubic forms. I'm going into no details. So the hope is that we can get an optimal result for how many variables do you need to solve a system of R cubic forms over QP. But before I've done that, can we still get something for free using the result above? The answer turns out to be yes. Using some methods that come from a paper of Wolfgang Schmidt and I in the early 1980s, one can prove the following. Suppose I have a system of R cubic forms over Q sub P in n variables. Then using this result here and some ideas from this early 1980s paper, if n is bigger than 27R cubed minus 18R, then there's a non-trivial common zero. So the best result up to now, as far as I know, would be Dietmann's result that if n is bigger than 125R cubed plus other stuff, and p different from 2. So that would be a nice consequence. And I think, and then for the special case R equals 2, which has also attracted attention, one gets that n bigger than 180 variables would be enough to solve a system of 2 cubic forms. And I believe the best, Rainer can tell me, that the best result would be Dietmann and Woolley proved that n bigger than 288 is enough. So these come relatively for free if this result up here holds. All right, so this concludes my talk. Thank you very much.
Thank you very much, David. Let's look for some comments and questions.
Rainer put in the chat, and that the 288 has been improved to 131 by Dumke. So I would love to see that reference if Rainer can supply that to me. I'm unaware of that. This is a minor point. That's not of this talk, but on the archive. Okay, I will look. I will. Thing is, okay, good.
Well, an obvious question here is you are using information of quadratics for cubics, isn't it, on your theorem?
Yeah, that's right. Okay, as I say, this has to do with a method, sort of an inductive procedure that Wolfgang Schmidt and I developed in the 1980s based on some ideas of Richard Brouwer in the 1940s. And yes, there's some, oh yes, and one other fact, that for one cubic form in more than 9 variables, and at least 10 variables, there's a non-trivial zero. So the idea is to use information about systems of quadratic forms and the one piece of information that one cubic form in 10 variables over a p-adic field has a non-trivial zero. Yeah.
Well, can we do this in an inductive method? Now I know for 2 and 3, I can do it for 4, 5, and
for cubic forms?
Yes, you're saying that you're doing this. You have information for cubics. for
Yes.
quadratic
That's the
and one
inductive
cubic.
method.
Uh-huh.
For a system of R cubic forms, one can use the fact, if you know about solving systems of arbitrary quadratic forms and one cubic form, then there's some inductive procedure to get some results, although probably weak, for a system of R cubic forms.
No, I'm asking you if I can do it. Now I have, following the same argument, I have a system, a result for a system of cubics, and maybe some information of one quartic form, then I can do it.
Yes. Yeah, it works in general. Yes.
Ah, wow.
Yeah. So that's in this paper, 1983 or something, with Schmidt and me.
Okay. When the system you put together and call this dense p-adic, well, I would say it's a parallel to the p normalization in a sense, to get some number. Yeah,
it's something you know very well. It's so-called normalization that you know when you're dealing with systems of additive forms. It's the exact same idea, but it works for forms in general. Yeah, that's right.
Okay.
Oh, yes.
Let's see if there are more questions. Oh, Dietman is giving you the precise address.
Thank you, Reiner. I appreciate it.
Do you have more questions and comments? Let's wait for a minute. For sure, it was a great talk and a great result.
Thank you.
Well, for sure, it was a great result. It's very impressive, David. I'm very impressed with all of this. It's such a quantity of great ideas. You know that, I don't know if I comment with you. I comment with you that Louis had always high praises about you, that you are a student with great and brilliant ideas. So it's easy to see that you deserve the praises.
It's an interesting subject to study, so it's a lot of fun.
Yeah. So let's thank David again.